Hi, we're the Husky Robotics team here at the University of Washington. As one of the first U.S. teams to feel the impact of COVID-19, Husky Robotics has put development of our 2021 Rover design on hold and focused on adding improvements to 2020's hindsight for this year's URC. With our recent new lab space, we have been able to continue safe but limited production to improve our end effectors, testing, science station, and software. Demonstrating our improved performance, our team focused on making hindsight to be light, powerful, functional, and reliable while maintaining our ability to do Rover soil analysis.
Hindsight's lightweight aluminum and polycarbonate body is mounted on a linked rocker system, conforming dynamically to the terrain for effective obstacle traversal. The chassis is driven and steered by 4 independent motors and is able to travel at a max speed of 1.1 meters a second and up max inclines of 40 degrees. The motor and gearboxes are sealed inside dual bearing housings within our tires, protected from dust and small rocks. Extensive SolidWorks simulations were conducted on the chassis to ensure that it can withstand both static and dynamic loading cases such as the 1-meter drop. The 3D printed wheel flanges are easily replaceable, engineered to be the point of failure in unexpected high shock load cases. To improve serviceability, we have made a standardized latch-based mounting system for rapid attachment of our modular systems.
After redesigning our arm for last year's competition and closely observing its performance, we've created a new iteration. We've replaced the side-mounted belt drive system with a sleek, internally mounted carbon fiber aluminum composite drive shaft. This isolates the moving parts and provides more room for mounting electronics, while still shifting the motor's mass towards the base of the arm to make the entire system more nimble.
In addition to keeping our Rover's competitive edge by improving in our science and software implementation, we are in the process of making a mock equipment servicing station to do practice runs with our operators, so we'll be better prepared, faster, and more efficient when we compete.
Our custom gearboxes have been integrated into the structure of the arm, and we've increased the gear ratios to provide more torque for better lifting and object manipulation during mission tasks. Overall, our design and manufacturing capabilities have allowed us to increase the dexterity of the arm while reducing its weight by 3%.
Our science station is equipped to determine the current or past viability of life on Mars. Our depth-selective auger deposits sample in a sealable container. For our soil analysis, we use a microscope, humidity probe, and a protein assay. The microscope provides information on geological composition and weathering. We use the Pierce 660 nanometer assay to detect proteins and biomolecules. The reagent is rapid responding and stable at room temperature for storage, transportation, and application. Our environmental sensor suite measures UV intensity, volatile organic compounds, CO2 concentrations, temperature, pressure, and humidity.
Our electronics team has been hard at work to make sure Hindsight systems are modular and reliable. Hindsight is controlled through custom embedded boards that handle power distribution, motor controls, and gathering telemetry, communicating with an NVIDIA Jetson controller over a CAN bus. Each board has integrated voltage, current, and temperature monitoring, and our custom CAN protocol emphasizes sending the status data to the Jetson and base station so we can monitor Hindsight and diagnose issues in the field. Additionally, the motor units contain PID control firmware that can maintain a given position or speed so the Jetson can keep focused on high-level control, video processing, and autonomous operation. This also facilitates inverse kinematics for controlling the arm. To reduce miswiring and the amount of wiring used for network communication, we have replaced wire connectors with stacking headers. For additional field contingency options, our boards are compatible with electronics designed for our 2019 Rover, allowing for additional modules and replacement if our spare boards aren't sufficient. Our modular approach means that we can use our motor and telemetry boards on our new tracking antenna to reduce development time and cost.
With limited access to the Rover, software's focus has been on improving our code base for Hindsight and future Rovers. We've written a new simulator to test our autonomous navigation algorithms. Here, the red triangles show the plan generated by weighted A-star search, which the Rover follows using the pure pursuit algorithm. The simulation models measurement noise and motion noise to ensure that our system is robust to real-world conditions. Hindsight localizes AR tags relative to the robot using OpenCV edge detection. Our algorithm is lighting agnostic to compensate for weather conditions. Finally, our web-based Rover interface displays camera feeds and has a dedicated dashboard for each URC mission.
Husky Robotics would like to thank all of its sponsors for their support.